welcome to this lunch seminar to disseminate or to present, let's say, the results of the Milestone projects. And we are the first off with this series. And it's the Milestone Project Crowd Movement about the prediction of pedestrian movement in cities. And it will be me who presents together with Stavroulaki and Anita Ullrich. And Anita Ullrich has been working with this project a lot, but we thought that today Franziska Hunger was going to present, but she was ill or had a child who was ill. So Anita will do that part of the presentation. So we will shift, let's say, who is talking. I will share my presentation. Let's do it like this. And then the big screen. You see my full screen now? Yeah, yes. Good. And what I said already is that this Milestone project was about modeling pedestrian movement. And there were quite some participants. As you see, the active participants are listed over here on this vertical list. But then there have been, during the course of the project, many more people from DTCC that has been involved. Just sort of an acknowledgement to those as well. And pedestrian movement, why do we look into that and why do we want to model and predict this? It has to do with the fact that, of course, let's say, pedestrian movement and walkability is a huge concern in the whole agenda of sustainable development, especially related to Goal 11, sustainable cities and communities. And this has to do with that let's say, if we walk more and use private cars less and increase public ridership, this will reduce greenhouse gas emissions. It increases, let's say, our active modes and therefore health and well-being. Also by being, let's say, sharing public space by walking, we also support social inclusion, cohesion, and that kinds of aspects. And it is a drive of local economies, people, let's say, being present at streets, promoting activities that can take place in the buildings along it. So there are many reasons, let's say, why it is important to actually be able to not only understand how the current situation is and where people move and not move, and where you have high intensity of people co-present in the public space and where not, it's also of high importance to actually be able to predict new situations. And that's where we have been sort of, we aim to do so. So it's really going to, from describing to predicting these flows of people in cities. And what we do in this project is to combine two approaches. There is one model that me and Jana have been working on a lot, and a lot of other researchers all over the world, which is looking at pedestrian movement from a network perspective, looking at the macroscopic models. Let's say it's on the city scale that you try to understand through the understanding of how the network is constituted and laid out, how that affects pedestrian movement. There are also examples to look into the pedestrian movement on a much more local scale, and there are different models, and we will use the social force model that Anita will talk about. But the innovation in this is not actually these two ways that we have sort of made a few steps forward in this project, but actually it's the combination of these two approaches that is the innovation of this Milestone project. So what we aim to do is, in a way, to predict pedestrian movement on this bigger scale so that we know which streets in the city have more pedestrians than others. And then we use that information to go to the local scale. It becomes an input variable for the local pedestrian predictions. And then we go over to a social force model and are able to predict the movement patterns in these local urban spaces. So that's the whole idea. And we will present this to you, let's say, step by step. And I will give the word to Jana to start with the city scale network model.
Yes, hello. So like we said, we start from the network model, which is the macroscopic modeling. And the aim of that is to predict numbers of pedestrians for every street in a neighborhood or in the city. So how many people walk on each street. But part of the aim is to do these predictions using special properties, special predictors that can be easily defined in an urban design and planning phases. And Meta will come back to that, because the point is that this modeling has to be useful to act upon the urban environment, to design, so to forecast pedestrian movement in situations that are planned, that we do not actually have, they're not existing situations necessarily. And the model we use is a machine learning model, a lasso regression model, indeed to start from a big list of predictor variables, but actually identify the ones that are most strongly associated with the response variable. In our case, it's the pedestrian counts. So what we did is that we trained the model using data gathered in Stockholm, the whole metropolitan area of Stockholm, using different neighborhoods, suburban neighborhoods, urban neighborhoods, and so on. So these were our training data. And then we tried to predict 75 street segments in Gothenburg Center. So that was our test. And we validated the model using real-world data that we had from Gothenburg Center. Next slide. Yes, exactly. So here we have the training data of Gothenburg, the validation data of Gothenburg that were collected from Traffic Contoret in 2018. And like I said, in our training data, we also had real world observations from different neighborhoods in the metropolitan area of Stockholm that we gathered in the smog in 2017. And the collection method was the same, which is important for comparative, to have a valid comparison. And it was capturing Wi-Fi signals from mobile phones. And next slide. Yes, so I will just give you the basic findings, the basic results. So when we predicted, like I said, 75 street segments in central Gothenburg, and the performance of the model was around 52% of the response variable we could predict. So that means the absolute volume of pedestrians observed, measured in each street, we could predict 50%, almost 52% of the response variable, which is a rough estimation, but sufficient for the early stage estimations of pedestrian counts. And like I said, the aim of the model was to only include special predictor variables, predictor variables that can be easily estimated, designed, calculated in the very early stages of an urban design and planning project. So from all this long list of variables that you see in the table, 40 or something, the significant variables are population density, network between a centrality, so street network centrality basically, accessibility to local markets, meaning service, retail, cafes, restaurant, pedestrian-oriented uses, and numbers of lanes and speed. And numbers of lanes and speed in this context describe the multimodal central street. So in a nutshell, multimodal central streets are associated with higher pedestrian counts. And what you see in the map, when we plotted the spatial distribution of errors, so to see which streets we could predict in a higher extent, we saw that the model basically fails to predict in a good way the highly active, commercially activated areas. So around Bruceparken, for example. So where the pedestrian counts have extremely high numbers. And this is a finding that we kind of confirms earlier finding from other empirical studies. And next slide. But apart from the prediction of the absolute numbers of pedestrians, what is specifically important for during an urban design and planning phase is if we can predict the distribution, the relative distribution of pedestrians. So it's not only about how many pedestrians we can predict on each street, but can we predict which streets will have more pedestrians than other streets. This is a very useful information in an urban design and planning phase, let's say, assessment. So such estimations can be very useful to guide these initial design phases in an urban development plan, to compare different design scenarios and strategies, and highlight missteps, potentials, to identify best ways forward, and so on. I will give the word to Anita, and Meta will come back to the usefulness again for urban design and planning. Anita.
Yes, thank you. So we heard about the modeling of pedestrian movement on the city scale, and we from the Fraunhofer Scheimer Center were specifically concerned with the modeling of pedestrian movement on the local scale, where we can resolve the individual movement of single pedestrians in the urban environment, as you can also see in the video shown to the right. And our model is based on the social force model, which is very common for pedestrian modeling with agent-based modeling and extensively applied, for example, for emergency evacuations from buildings. And the input data for the pedestrian amount in these simulations can be based on measurements or statistics or rules of thumb, or in our case of the coupled model, from the input or from the data that we retrieve from the network model, like the number of pedestrians that we can expect on each street segment. Yeah, next slide. So our framework is based on the core technology of Demify, which is a particle simulation software for discrete element method simulations. And here we can simulate the individual particles, which in this case are pedestrians, and have the microscale information available at each time step. And Demify facilitates the efficient detection of pedestrians which are close to each other, and the detection of pedestrians that are close to obstacles in the way or geometries like buildings, benches, statues, trees, and so on. And in this solver, we can or the time evolution in the solver is based on the forces that are acting on the pedestrians and affecting their movement. And to implement the social force models, we extended the software Demify with Python extensions. And here we implemented, as I said, a social force model, which is acting between two pedestrians that are close to each other, but also between pedestrians and obstacles to just ensure a certain distance between them. Then we have the motive force, which drives the pedestrians towards their desired destination in a simulation, such that they start moving there. And additionally, we included a line of sight guidance, such that the pedestrians can actually see obstacles in their way and adjust their path to avoid running into the obstacles, but going around them. And additionally, we also added a velocity adaptation for tilting floors, such that pedestrians move slightly faster when they move downhill and a bit slower when they move uphill, for example. And as an behavioral extension, we also added a curiosity module, such that you can define different attraction points, such as shopping windows or store windows, where pedestrians can get attracted to, such that a pedestrian could deviate from their original path, stop and look for a second, and then move on with their original path. Next slide, thanks. Yeah, we compared our agent-based model to real-world measurements based on a data set that we got from Viscando for the area Nordstern in Gothenburg, where we retrieved from the real-world data the pedestrian trajectories, people counts at the marked lines, as you can see in the lower plot, the dashed and the solid line, and the mean velocities of the pedestrians for different time intervals. And the simulation input from the recordings were the flow rates of the pedestrians entering the domain at the different sections, which were here north, crosswalk, mall, and south, as you can see in the graphic, which we then used to assign each pedestrian their origin and destination based on an origin and destination matrix. And yeah.
Oh, sorry. Sorry.
No, I just wanted to say that you can see the trajectory plots compared between the simulation and the measurements here to the upper right. Now we can move on. Thanks. So now we have the two models in place, the network model on the city scale and the agent-based model on the local scale. And the innovation in this project, as Meta said, is the connection of both in a hybrid model, where we first simulate the aggregated flows of the people moving in the urban area with the network model, and then take this input to simulate the individuals moving in the urban area with the microscale local scale model. And the input in more detail is the initial distribution of individuals, how many pedestrians we can expect, and the origin destination matrix, meaning the incoming and outgoing individuals at the domain boundaries that we consider. And this facilitates scenario testing, for example, for urban planners, where we can have other input data, such as the velocity distribution, to steer the desired speed of pedestrians, where they walk or that they find comfortable, the attractiveness of points along the path, like shopping windows or statues or a cinema or something else, and the modeling of further individual behavior. Yes, next slide. And to evaluate the hybrid model, so the connection of both of the models, we considered the case of the Kungstorget region in Gothenburg, where we also had datasets of Iskander available, also including pedestrian trajectories and pedestrian counts, as well as their velocities. And here we utilized the network model to create full day predictions of the pedestrians to be expected on the street segments. And based on this information, we prescribed the flow rate of pedestrians entering the domain and the origin destination matrix in the local scale model. And the domains that we chose in this case are seen in the picture above to the right, where we have 6 different sections where pedestrians can enter and leave the domain. Yes, next. So here to the right, you can see a comparison of the results of the hybrid model and the real-world measurements. The simulation results are shown on the left, and the real-world measurements on the right. And in the first row, you can see the trajectories of the pedestrians, and in the second row, a heat map of the pedestrian densities in the area. And we can see that we capture like the main structures of the real-world data. But of course, the real-world data is much more chaotic than the simulation results, but this could be more refined to achieve a similar chaotic behavior of the pedestrians. But we can see that we have similar densities and also similar areas of the domain that are frequently used by pedestrians. So advantages of our hybrid model are that we can actually resolve the local behavior of individual pedestrians, and we can evaluate properties of the pedestrian flow, such as the velocity or personal space. Next slide. Here, for example, you can see a plot of the distance between pedestrians when they are in a conflict, and a conflict means that they are closer than a certain distance. So we consider if, so we are computing the social force between them to ensure that they keep a certain distance. And here we can see how many of those pedestrians that are close to each other actually have a distance of below 1.5 and below 1 meters. And below 1 meters, we would consider already a violation of the personal space. So we can actually see that with this pedestrian densities, we can see quite some violations of the personal space in the pedestrian movement. But this is also, of course, a definition question, but this can be evaluated by urban planners. And for example, if the layout is redesigned, this could be, this could be reduced or increased. For example, how many people are experiencing a violation of personal space. So furthermore, we facilitate the scenario testing, which implies that we can test specific behavioral rules, such as a larger distance between individuals that they want to keep up. We could model elderly, disabled, or running people. And the extension with behavioral rules is easy in the Python extension that we implemented. And also we get a comprehensive visualization in urban planning. Next slide, which you can see in this video here, which really facilitates or which really improves the dialogue of urban planners. If you have if you can show the pedestrian movement in this way. So it's suitable for the design comparison for public spaces as well. However, a disadvantage of this hybrid model is that refining the model setup to real-world behavior, such as this chaotic behavior that we saw in the real-world measurement plots, it can become cumbersome because it's quite detailed work and you need to have rules of thumb in place how the pedestrians should behave. So thank you, and now I'll give the word back to Meta.
Thank you, Anita. So I will kind of wrap up by taking the step also to how this could be used in planning practice. And we have done a few workshops to test this where Lilje Wall has been leading. And in the first place, we sort of tried to assess how could this be used. And one thing is, of course, to understand the current situation. So we have talked a lot about the prediction of, let's say, new situation, but actually there is a lot to win already by understanding the current situation and to know what you want to change or how you could react on that. And also it could be very useful to validate assumptions that you have. You think certain paths or certain streets are used more frequently, and you could sort of validate that. But the most sort of crucial things what we have referred to a lot is the comparison of scenarios, so design alternatives in an early stage. And finally, there is, of course, a possibility to assess, let's say, afterwards, whether your design approach, let's say if you would do observations after implementation, see how it affected. And I put another, which we have discussed a lot in this project, another diagram here on the right. And this is what Jana was referring to earlier. There is a huge, let's say it's very important to understand that if to make this kind of information useful in planning practice, you need to have this information very early in the design process, because the later it comes, the harder it is to change and the more costly it is to make changes. So the earlier you have this kind of information, the better, which requires that the model should be kind of simple and not include variables and things that you do not know in the early stages of a design process. So you want to become, let's say, in the time perspective, this horizontal axis, you want to be as early as possible. And we have been, especially in the network model, pushing towards, let's say, to make this, to include the variables that are known so early in the design process. So this is something we have discussed a lot. And we have looked into a few use cases. Let's say how could you actually use this setup, this hybrid model? And I took with me two examples. One is, let's say you have a new design and you are actually thinking, where should we put the entrances of a new building? And this has effect, let's say, I mean, first you could react on the flows that you know from the network model. So the model that sort of shows the pedestrian flows on the bigger scale. But then you can also test with the local, with the force model that Anita has been showing, that if you position the entrances somewhere, then this will also affect pedestrian movement patterns. So actually you can use it in two stages in this case. So that's one very clear example that we looked into, and we describe, let's say, this understanding the situation and do comparisons, but I will not go into details here, because we will not manage in time. But the other example is of another kind. It's, for instance, where you have a location and you are thinking about, okay, where you will add a new bridge or that can be over the river or over a highway or something. So you are wondering, where should we put it and what would the effects be of that new position of a bridge tunnel over some kind of barrier. And of course, in that case, it is also very useful to have this hybrid model to see both how the larger scale pedestrian flows will change due to this new bridge that you put somewhere, and then also look into specific public spaces that will be affected by that in the microscopic model. So these are two examples that, let's say, are to showcase, let's say, how this could be used. Then to finish up, we have published a research report. And that's the first one that I put here. So there you can actually read about the whole, let's say, the whole package of things that we have been doing. And we have one paper, that's the second one here, which is in review at the moment. It's almost there. And the third paper is a conference paper that will be presented in June 2024 at the Space Syntax Conference. And most probably we will bring this further into a journal publication later on. So those are the results of in terms of products, let's say, besides the models that we have developed, of course, which are also important products. I think that was it. So let's see if there are questions, but thank you for listening. I will stop sharing and see if we have some questions.
Thank you. I have a question for if no one else is before me. Ioanna, you said you got 50% prediction, right? So could you, are you thinking about other prediction variables that you could include to improve that? Are you missing something that you would like to put into the model?
Well, yes, and this is kind of a constant results we have been getting, that when we lean only on spatial variables, there is a kind of a ceiling that we hit. We need to start adding perhaps more other types, socioeconomic variables and so on. We make a choice to not do that now because, as Meta said, we need to have variables that we can estimate in early stages of a design process. But yes, if one would want to reach higher prediction performance, we need other variables, and it will probably not be spatial, because with the spatial variables, I think we have tested a very high number.
Yeah.
Different alternatives.
Yeah. And maybe it's good to add, let's say there are models out there that are including all these kind of more socioeconomic information, etc. And they get to higher prediction levels. But the problem is that you will never be able to use that in the early stages of a design process. So there's, let's say, it's kind of a balancing act here.
Exactly. And we have this discussion with traffic people from traffic modeling, for example. And there they have these super complex models that reach a very high prediction levels, but they themselves understand the limitation of how to use this in new situations, planned areas where you don't have this information.
Okay.
Okay. Other questions or comments?
Yeah, I have one more.
Yeah, go ahead, Anders. You're welcome.
So for Anita, I mean, you're using Demify, which I know quite well. So I mean, it's typically used for industrial applications where you have several 100,000 rocks and things that bounce at each other, gravel, and it's like 100,000 contacts in each time step that need to be handled. And here, I guess there are many fewer collisions. So I guess you're not really using, the full power of Demify. I mean, this must be an easy problem for Demify. Is that correct?
Yes, that is correct. So as you say, usually we are more concerned with tens or hundreds of thousands of particles. And in this case, we have many less. We have like hundreds of pedestrians maybe in the domain at the same time, at least for the simulations that we consider so far. But I think, so yes, we don't utilize the full capacity of Demify, but we still utilize like the sufficient contact detection where we don't have to, since the particles are spread over a quite large domain and pedestrian movement, and there's a lot of room between them. The algorithm for contact detection that is implemented in Demify is actually really handy for these cases. So this one we utilize, I would say, still for full capacity.
Great. Yeah, thanks.
Good. I have Graham.
Yes, you mentioned modeling individual pedestrians as particles. I was wondering about family groups of friends who might be a wider group possibly moving more slowly. Does the model include those?
That's a very good question. We don't include it currently because we tried also to keep the model as basic as possible. But it's definitely something that we considered and discussed, and it could be implemented as an extension, but we don't have it in place right now.
Okay, thank you.
Good. Then if there are no
Can I
more
add something?
Yeah, Jana, go ahead. Sorry.
In terms of publications, because we also try to, you know, make things a bit open source. So the code also of the network model is on GitHub. So one can, so that these are important outcomes, I would say, also
great. Yes.
open access things and so on. So we are working towards that as well.
Okay, right. Very good, Jana. I think I can add that to the let's say to the presentation. And then we can distribute the presentation so that you can find the things that we have developed. Yeah. But then very good. Thank you, Anita and Jana, for joining the presentation today, and you all for listening to us. And please look into our work. There's a lot to read more about this. And thank you for participating. Don't forget to come to the next one as well. I don't know when it is, but in 3 weeks' time, I think.
So have a great day, everyone. Great weekend.